Swayam Prabha. Digital India. Educated India.
Good morning and welcome to the lecture number 14 of the course Stochastic Hydrology. If you recall, in the last lecture we covered essentially the details of frequency domain analysis. We introduced in that course how we convert the data in the time domain to frequency domain, and we introduced the concept of spectral density. And from the spectral density diagram, which is typically called as a line spectrum, or the smoothened spectrum is also called as the power spectrum. From this we identify periodicities inherent in the data, and then we also introduced the tests, the statistical tests for testing which of these periodicities that we identify through spectral analysis are in fact statistically significant. And then once we identify the statistically significant periodicities, we also examined how we remove those periodicities from the data. And then in that process we also introduced a method of standardizing the data. We examined what happens by standardizing the data, how the correlogram looks, and how the spectral density or the line spectrum or the power spectrum looks for the standardized data vis-a-vis those for the original data. Towards the end of the last lecture, we were discussing a numerical example of estimating the power spectrum and identifying the periodicities. So, we will continue with that example. So, we considered the data for monthly stream flows at a location in that example. So, we will first recapitulate significant features of the frequency domain analysis. As I just mentioned, spectral density spectral analysis helps us identify significant periodicities in the data. The correlogram gives us an idea that yes, periodicities are present in this data, and then the spectral analysis helps us identify which of these periodicities are in fact significant. The spectral density, as we introduced, it is also called as a variance spectral density. It gives the amount of variance per interval of frequency. A peak in the spectrum or the spikes like this, for example, you may get spikes like this. These spikes correspond to periodicities in the data. So, the W value, the omega value that we get corresponding to these peaks here, they correspond to the periodicities inherent in the data. The line spectrum, as we introduced in the last lecture, is an inconsistent estimate, statistically inconsistent estimate, whereas the power spectrum or the smoother spectrum, which is shown here, is a statistically consistent estimate. So, we will continue with the example that we were discussing in the last class. We are considering the monthly stream flow, which is given in QMEX. These are available for 1979 to 2008. So, there are a total of 348 values. Only just a few values are shown here, just to give you an idea of how the time series is arranged. So, for example, June, July, August, etc., it keeps on going until May of the next year, and we have the corresponding flows. Like this 1 to 12, it keeps going until n is equal to 348. 13, for example, corresponds to the month June. Similarly, 25 corresponds to month June, etc. So, the time t here goes from 1 to 348, but there is also an associated month index June, July, August, etc., which is important when we go to standardization. We will revisit this again at that point. So, we had a time series plot. So, you have 348 values for the time series. The moment you plot the, you will realize that there must be a periodicity, because you are seeing significant peaks here time series itself at regular intervals. So, this information we look at more closely through the correlogram, and correlogram and spectral analysis I have shown in the last class. Let us see what happens to the time series when we standardize. Let t, if you recall, what we did in the last lecture is that we identified periodicities in the data through spectral analysis. We saw that there were several peaks, peak corresponding to 12 months, corresponding to 6 months, 4 months, 3 months, and so on. So, we wanted to examine what happens to the series when we remove the first two periodicities from the data. So, we reconstruct the time series as z t is equal to x t minus y t, where x t is your original series and y t is the series corresponding to the first two periodicities. So, this is in the frequency domain. The first two periodicities are here, alpha 1 and beta 1, alpha 2 and beta 2, omega 1 and omega 2. So, this term corresponds to the first two periodicities in the frequency domain. So, we reconstitute the time series in the frequency domain as z t is equal to x t minus y t, remove the first two periodicities and plot the time series. Look at how the time series looks vis-a-vis the original time series. The original time series is here, this is your x t and this is your z t. So, the regularity of the peaks that we were seeing has now diminished. So, this is when we removed the first two periodicities. Let us see how the correlogram and the spectral density of this new series looks. The original data had a correlogram like this, indicating presence of a significant periodicity. As you can see, the correlogram is oscillating regularly, and then if you take it further, let us say you have 348 values, maybe if you go up to 200 or some such thing, you will see that it is slowly decaying as time progresses. With respect to lag, the correlogram slowly decays. For the z t, if you plot the correlogram, here the significance levels were somewhere around 0.1 here. So, most of these correlations were significant, statistically significant. If you plot the correlogram of z t from which the first two periodicities have been removed, this is how it looks. Most of the correlations are now insignificant. However, there are some significant correlations at regular intervals, as you can see. So, you again suspect that there may be some periodicity still inherent in this z t. That means, even after you remove the first two periodicities, there may be some periodicities still inherent in the new series z t. To examine this, we plot the spectral density of the new series z t. So, let us see how it looks. As you can see here, the periodicities which were inherent, this is the power spectrum for the original data, this is the power spectrum for the z t, which is the transformed data in which the first two periodicity from the original data have been removed. So, you had a periodicity of somewhere near 0.5 and somewhere near 1.1 or some such thing, those are absent here. These periodicities have been removed, and the periodicities corresponding to the 4 months and the 3 months. This was for 12 months, this was for 6 months and 4 months and 3 months. These become prominent now. So, somewhere around 1.6 or something, you had a spike here in the original data, that becomes prominent, and similarly somewhere around 2.2 or something you had a peak here, and that becomes prominent. So, like this, when you remove the periodicities, now you can remove this periodicity from ZT using the same transformation that we use for on XT to determine ZT. Similarly, on ZT you remove this periodicity, then you will see that this periodicity becomes more prominent, and then if there are any other periodicities downstream of that, that will become prominent and so on. So, this is how you will examine visually whether you still have any periodicities present in the data. Now, whether the periodicity that you have just determined is significant or not is a different story, that we will check it with statistical tests, but that this periodicity is in fact present in the data itself becomes apparent once you remove the periodicities that you have already identified earlier. So, now we will do the statistical tests to examine whether a particular periodicity is significant or not. In the original series, when we plotted the power spectrum, you had a peak corresponding to a W value of 0.5236. Now, this is 0.5236, and we have seen that for the monthly data, this periodicity corresponds to a periodicity of 12 months, simply 2 pi by omega p. Now, we will examine whether this is statistically significant or not. To do that, what do? We form the statistic gamma square n minus 2 by 4 rho 1 cap, where rho 1 is estimated or rho 1 cap is 1 by n x t, which is your original data, alpha cap, which is the alpha corresponding to the particular periodicity that you are examining. So, for the first peak we had omega 1 is equal to 0.5236 and alpha 1 is equal to 29.28 and beta 1 is equal to 172.93, which we had estimated in the last lecture. So, these are the values that we had towards the end of the last lecture. So, this omega is for that particular k that you are examining. So, you are examining for the first periodicity. So, you will take omega 1 and beta and alpha correspond to the same periodicity. So, alpha 1 and beta 1 you take. So, you can estimate rho 1 cap, n is the total number of values that you have, in this case it will be 348. So, gamma square here is simply alpha square plus beta square, you will get alpha square plus beta square is equal to 30762 and rho 1 cap you estimate from his. So, rho 1 cap is equal to 1 by 348 and all of this term together will be 36810. So, it is 105.78 and from that you estimate this statistic gamma square n minus 2 by 4 rho 1 cap. So, n is 348. So, you will get 25,155. With this value you go to the F distribution tables, which are available in any standard textbooks. Corresponding to 95% value, 95% significance level, you get F with 2 degrees of freedom and for n minus 2 as 346, you will get a value of 3.0. If the value of the statistic that you have calculated is more than 3.0, it indicates that the corresponding periodicity, in this case the first periodicity corresponding to omega 1 is in fact statistically significant. So, in this particular case 25,000 is far ahead, far more than the corresponding F value here for 95% significance level, and therefore, the periodicity corresponding to your value of omega 1 of 0.5236, which corresponds to a periodicity of 12 months, is in fact statistically significant. So, the periodicity that we have just examined is statistically significant. Similarly, we do it for other periodicities. As you can see here, after the first peak you have a second peak corresponding to this value of omega 1, omega 2 and this value corresponding to omega 3, etc. So, these things also we examine one at a time. Remember here this statistic is written only for a particular value of omega. So, every time you test one periodicity at a time. When you do that, you will get the values of statistic like this 11,000, 4,000, 1295 and so on. So, all of these are much above the critical value of f, and therefore, they are all statistically significant. Now, having identified that these periodicities, this corresponds to 12 months, this to 6 months, this to 4 months and this to 3 months. Having identified that these periodicities in the data are statistically significant, we now want to see how to remove these periodicities from the data. As I mentioned in the last lecture, one simple way of doing this is simply remove the periodicities by standardization, simply standardize the data, that is z t is equal to x t minus x bar over sigma or x t minus mu over sigma. Let us see what happens to the original time series, the time series plot, correlogram and the spectral density when we remove the periodicity by standardizing. So, let us look at the standardized time series. So, what we are now doing is we are transforming the original series into a standardized one. We write, because we have used the notation z t earlier in the same problem. So, we will write this as z dash t, which is the standardized time series, x t minus x I bar over S I. The I here corresponds to the particular month to which t belongs. As I mentioned earlier, t goes from 1, 2, 3 etcetera up to 348, which are the total number of values. But corresponding to every t, we have an I which identifies it with the particular month. For example, t is equal to 1 corresponds to I is equal to 1, t is equal to 3 corresponds to I is equal to 3, t is equal to 13 corresponds to I is equal to 1 again, t is equal to 14 to I is equal to 2 and so on. So, we identify the month to which the time period t belongs and deduct the particular mean of that particular month. June has its own mean. So, you deduct the mean of June when you are taking I is equal to 1 and so on, and similarly the standard deviation corresponding to that particular month. So, we formulate z dash t by this particular transformation. So, the original time series x t is now transformed into z dash t, and for example, you are looking at the first value x 1. For the first value, you deduct the mean of June month and standard divided by standard deviation 52.24 and so on for this month June. Similarly, 2 you take the July month, 3 you take the August month and so on, 13 again you take June month, 14 July month and so on. So, like this you formulate the z dash series. This is called as the standardized series. This is one way of standardizing, where you deduct the mean and divide by the standard deviation. So, you have now ready with you the z dash series. So, z dash series for example, looks like this as just the first year values I have shown, first 12 months. So, x t and z dash t. So, z dash t series is like this. So, you will have 348 values of z dash t for t is equal to 1 to 346, 348. We will do the spectral analysis on this new series now z dash t and see how it looks vis-a-vis the spectral density figure or spectral diagrams of the original time series x t. So, the time series when you plot for the standardized data, it looks like this, whereas the original time series was this. So, this is the standardized data, time series for the standardized data. This flow is standardized flow. as you can see here, this is a much more random series compared to the original time series. The original time series had some periodicities and so on. So, you see some regularity in the original time series, whereas by standardizing you are seeing a much more random series here. But whether it is truly random or whether there are still inherent periodicities in this etcetera, can be seen only if you plot a correlogram, plot the correlogram of this series and do the spectral analysis on this series. Let us do that now. So, if you plot the correlogram, your original correlogram looked like this, that is the correlogram of the original time series looks like this, and the standardized time series, when you do the correlogram, this looks like this. So, most of the correlations are statistically insignificant here. So, the periodicity seems to have been removed in the standardized series, but this can be verified through the spectral density. So, the correlogram shows that yes, the statistically significant periodicities have all been removed, and most of the correlations here except for the really early ones, they are all statistically insignificant. This information can be seen better in the spectral density. So, if you look at the spectral density, this is how it looks. In your original series, the power spectrum looked like this. The power spectrum of the original series showed significant spikes corresponding to the periodicities of 12 months, 6 months, 4 months and 3 months here, whereas the spectrum of the standardized data looks much more random here. No single periodicity or no single spectral density is any more different from any other periodicity here, and therefore, the variance is spread more or less uniformly, as you can see from the spectral density of the standardized data. So, standardization removes the periodicities present in the data, but this may not be always true. So, you need to really examine, after standardizing the data, you need to examine whether the periodicities have in fact been removed by doing the transformation corresponding to standardization. For example, you may have daily rainfall data. What we have done just now is for the monthly stream flow data, which is much more smoothened process corresponding compared to the daily rainfall data. For example, if you have daily rainfall data with several zeros and then once in a while it rains, but it rains very heavily during that time period, and then this may have a long term periodicities present in the data. If you are then looking at standardization with respect to the daily mean and the daily standard deviation, the periodicity, the long term periodicities that are present in the data may not be removed. We will see some applications of the spectral density towards the end of this course, where I will be dealing with only the applications of all the topics that we have covered in the course. During that time, we will see how the rainfall time series behaves, how the monthly stream flow time series behaves, how aggregating the rainfall over season and then looking at seasonal time series of the rainfall will be much different from the spectral densities and the correlations of the daily time series and so on. So, the information content in the time series comes to the surface by doing all these analysis. So, the inherent information that we have in the time series comes to the surface through the correlogram, through the power spectrum and so on. So, what we have just examined is that the periodicities that were significantly shown up in the original time series have been removed by doing the standardization. So, standardization is one way of removing the periodicities. So, we see that corresponding to this value, we had a significant periodicity. So, we will check again corresponding to that value of omega k whether the periodicity is present or not. So, we again recalculate the statistic as we defined here earlier. We calculate this statistic gamma square n minus 2 by 4 rho 1 cap, and then corresponding to this omega 1, we test the statistic value comes out to be minus 4.7 e to the power minus 12, very low values, very insignificant values compared to the critical value of f, which is 3.0, which shows that any of these periodicities are statistically insignificant, or they can be taken to be absent in the data. So, the periodicities are insignificant. So, essentially what we have tested this through the exercise that we just did is that in the original time series we saw some periodicities which were all statistically significant. We standardized the data and re-examined to make sure that the periodicities that were present corresponding to 12 months, 6 months and 3 months have all been removed from the data, by ensuring that the periodicities corresponding to this are all statistically insignificant. Now, we will go to an interesting topic in the time series analysis. These are the models that we will be dealing with now onwards are called as ARIMA models, auto-regressive integrated moving average models. Now, these are Box-Jenkins type models, and they are very popularly used in hydrology, especially for modeling monthly flows, seasonal flows and such other processes which are of interest in hydrology, most hydrologic applications, where we want to use these models for forecasting as well as generation of the models, data generation. Recall that we introduced a model earlier on, maybe about 3 lectures ago, for data generation using the first order Markov process, and that we also called it as non-stationary first order Markov process. We will see that that was in fact an autoregressive model when we looked only at the stationary model. So, before we went on to the non-stationary model, we introduced the primary stationary model that in fact turns out to be the first order autoregressive model. So, the ARIMA models we use extensively in hydrology for data generation as well as for real time forecasting models. So, we will just over the next half an hour and also over the next lecture, we will deal mostly with the ARIMA type of models. Let us look at what we did in our regression. Let us say that you are looking at the flow at a particular location, which is governed by this catchment, and we called this variable as y, and there were several variables. For example, rainfall was one of the variable, soil moisture may be another variable, your catchment slope or vegetation may be another variable, and so on. Antecedent moisture which I just mentioned as a soil moisture, that may be another variable. There may be several other variables, for example, evapotranspiration may be another variable and so on. So, we were essentially looking at the relationship between the runoff at this location with several different physical variables. That is what we did in regression. Actually, the regression that I introduced was only simple regression in which only one variable was considered, but subsequently we will also deal with multiple regression in which the dependent variable will be governed by several independent variables like x 1, x 2, x 3. For example, as I said, rainfall, soil moisture, evapotranspiration and vegetation and so on. So, you may have several variables, all of which determine the variation in y. This is called as whenever we talk about regression, we generally understand that you are regressing one variable with other variables. In the auto regression, what we do is we are regressing the variable upon itself, but the values that the variable has taken at different time periods. So, for example, you are talking about x t being dependent upon x t minus 1, x t minus 2, x t minus 3, etcetera. So, you are not talking about different variables, you are talking about the same variable, for example, the flow at a particular location, but the flow at a particular location at different time periods t minus 1, t minus 2, etcetera. For example, this may be June month's flow, this may be May, this may be April, March, February and so on. So, you are talking about a single variable, but the values taken by that variable at different time periods. So, that is called as auto regression. Let us say you are talking about auto regression of first order. We may simply write x t is equal to some constant phi 1 into x t minus 1, which is the flow. If x t denotes the flow at time period t, you are regressing x t with x t minus 1, the flow during the previous time period, plus there is a error term or the random noise term here. So, this is the random component or noise or residual. So, you write x t is equal to phi 1 into x t minus 1 plus epsilon t, which is similar to what we did in regression. Simple linear regression, what did we write? Y is equal to a x plus b. So, similar way we are writing x t is equal to phi 1 x t minus 1 into plus epsilon t. This is a simple AR1 model. Let us say you are writing autoregressive model of order 2. So, you will write x t, that means when you are talking about order 2, you are saying x t depends on x t minus 1 as well as x t minus 2. So, two terms behind you are taking. So, you will write AR2 model as x t is equal to phi 1 x t minus 1 plus phi 2 x t minus 2 plus epsilon t. This is similar to writing a multiple regression model, multiple linear regression model of the type y is equal to a 1 x 1 plus a 2 x 2 plus b plus some other constant b. So, in the autoregressive 2 model, you will write the model in terms of the two previous values x t minus 1 and x t minus 2. And like this, you write a general ARP model, autoregressive model of order p, by taking into account the previous terms. So, x t is equal to phi 1 x t minus 1 plus phi 2 x t minus 2 etcetera, phi p x t minus p plus epsilon t. So, if x t denotes the flow at a particular month, let us say you are talking about the stream flow in the month of June, and this is the monthly time series, you may write that as phi 1 x t minus 1. Let us say you are talking about phi 12 x 12 is equal to phi 1 x 11 plus phi 2 x 10 and so on. So, you are taking previous terms. So, you write this in a more compact form as x t is equal to j is equal to 1 to p phi j x t minus j plus epsilon t. These phi j's are called as AR parameters. So, the phi j are called as the autoregressive parameters. So, given any model of this type, we should be able to estimate phi 1, phi 2 etcetera from the data. So, you have the data on x t, you write a model like this. So, there must be a way of estimating these parameters, which we will see subsequently how we do this. Similar to the correlation that we talked about, we have a very important concept called as partial autocorrelation. It is denoted as PAC. Before we go into a more generalized ARIMA model explanation, let us see what we mean by PAC. What did the correlation coefficient indicate? The correlation coefficient between two variables, the correlation between two variables indicates the linear dependence of one variable on the other. For example, if we say that rho 1 is equal to 0.6 between x and y, or the correlation between x and y is 0.6, it indicates the degree of dependence between of y on x. Now, the partial autocorrelation indicates the dependence of one variable x t on x t minus k. We are talking about autocorrelation, and therefore, the same variable we are talking at various time periods x t on x t minus k, when the dependence on all other variables x t minus 1, x t minus 2, etcetera, x t minus k minus 1 are all removed. What we mean by this is that when you are talking about dependence of x t on x t minus k, all these other dependents, the correlation when we are talking about x t on x t minus k, these dependents are also included in that. But if you have some mechanism by which you will partial out or you remove the dependence of x t on x t minus 1, x t minus 2, etcetera, on all other variables except x t minus k, then the remaining correlation is in fact the partial autocorrelation. So, it indicates the dependence on x t minus k alone when the dependence of x t on all other variables has been removed. To understand this better, let us say that y is regressed upon x 1 and x 2, and then we are interested in how much explanatory power x 1 has if the effect of x 2 is partialed out or removed. That means, y is dependent on x 1 as well as x 2. So, you have regressed upon y upon x 1 and x 2 both together, but now you ask the question, out of x 1 and x 2 how much power x 1 alone has. How do we answer this question? Let us say that y we regress only on x 2 first and get the residuals out of that. That means, x 2 has been able to explain part of variance of y, the residuals we take out, and then the residuals we regress with respect to x 1, and then see how much of these errors or these residuals can be explained by x 1, and that is in fact the explanatory power of x 1 on y when the dependence of x 2 has been taken out, when the correlation on x 2 has been taken out on this. So, this generally gives the idea of the partial autocorrelations. Now, the partial autocorrelations are an important indicators of what type of ARIMA models that we may use for the data that we have, and therefore, we must be able to estimate the partial autocorrelations and infer from the partial autocorrelations what level of autoregressive terms that we may want to use for our models. The partial autocorrelations, this is what I just explained. For example, if you have y is equal to f of x 1 comma x 2, first you regress only x 2, then you get the error terms and then regress x 1 on the error terms that you get. So, you will be able to tell how much of the relationship is being explained by x 1 alone, how much of this relationship is being explained by x 1 alone, and that indicates the partial autocorrelation. The AR1 model that we wrote as x t is equal to phi 1 x t minus 1 plus epsilon t, because you are dealing with only one variable x t and x t minus 1, that is x t on x t minus 1, you are regressing x t on x t minus 1. The term phi 1 here explains completely the explanatory power, provides completely the explanatory power of x t minus 1 on x t, and therefore, that itself becomes the partial autocorrelation for order 1 of order 1. So, phi 1 of the AR1 model is in fact the PAC or the partial autocorrelation of order 1. Let us write AR2 now. AR2 we write it as x t is equal to phi 1 x t minus 1 plus phi 2 x t minus 2 plus epsilon t. For the AR2 model, phi 2 is the partial autocorrelation of order 2. Remember, the phi 1 of AR2 model is different from the phi 1 of AR1 model, and the phi 1 of AR2 model does not, I repeat, does not indicate the partial autocorrelation of order 1. If you want the partial autocorrelation of order 1, look at the AR1 model, the phi 1 of AR1 model is the partial autocorrelation of order 1. If you want phi 2 or the partial autocorrelation of order 2, you write the AR2 model, and the phi 2 that you write here for the AR2 model is in fact the partial autocorrelation of order 2. So, in general the phi p of the ARP model indicates the partial autocorrelation of order p. So, any ARP model you write like this: x t is equal to phi 1 x t minus 1 etcetera, phi p x t minus p plus epsilon t. The phi p of the ARP model is the PSE of order p. There is an elegant way of estimating the partial autocorrelations. We have introduced earlier in one of the earlier lectures the Yule-Walker equations. We use the Yule-Walker equations to obtain the phi p or the partial autocorrelations. If you recall, the Yule-Walker equations we wrote as P p, which is the autocorrelation function of order p, into phi p, which is the partial autocorrelation, is equal to rho p, which is the lag 1 these are just the autocorrelations. So, if you write this in the long form, this is your P p or the what we call them as autocorrelation function. So, the autocorrelation function is 1 rho 1 rho 2 etcetera rho n minus 1, like this it goes, and similarly this has to be P, I am sorry, this has to be P here. This is P by P. So, similarly phi 1 phi 2 etcetera up to phi p. Just half a minute, I will just change the pen. Okay. So, this is rho p minus 1, this is rho p minus 1 etcetera rho p minus 2 and rho 1. Similarly, phi 1 phi 2 etcetera phi p, and this will be equal to rho 1 rho 2 etcetera rho p. So, this is the pth order Yule-Walker equation. So, when you solve this pth order Yule-Walker equation, you will get the solutions for phi 1 phi 2 etcetera phi p, and the phi p, which is the last term that you get, is in fact the partial autocorrelation of the order p. So, this is how you determine the partial autocorrelations of order p. If you want phi 1, you write the Yule-Walker equation for of order 1. If you want phi 2, solve Yule-Walker equations of order 2 and so on. So, this is the pth order Yule-Walker equations. So, for PSE of order 1, you write the Yule-Walker equation of order 1, which is only one term. Here you will write the first term, which is 1 here, and then phi 1 is equal to rho 1. Therefore, the first partial autocorrelation is equal to the lag 1 autocorrelation itself. So, phi 1 is equal to rho 1. Similarly, for the second order partial autocorrelation, you will write the Yule-Walker equations of order 2, which is 1 rho 1 rho 1 1. What I am doing now is that I am writing it for the second order. So, 1 rho 1 and rho 1 1 is equal to into phi 1 phi 2 is equal to rho 1 rho 2. That is a second order equation. So, I will write this as 1 rho 1 rho 1 1 phi 1 phi 2 is equal to rho 1 rho 2. When we simplify this, I am multiplying this. So, phi 1 plus rho 1 phi 2 is equal to rho 1, that is the first equation. Similarly, rho 1 phi 1 plus phi 2 is equal to rho 2, that is the second equation. So, you have two equations, rho 1 and rho 2 are known, you can determine phi 1 and phi 2. Rho 1 and rho 2 are the lag 1 and lag 2 autocorrelations. These are determined from the data. So, from data you know rho 1 and rho 2, and therefore, you should be able to solve this simultaneously and get phi 1 and phi 2. So, we will simplify that you write phi 1 plus rho 1 rho 2 minus phi 1 rho 1 phi 1 is equal to rho 1. This is from this equation. You get here phi 1 plus rho 1 phi 2 is equal to rho 1. So, you are putting it for phi 2 here, substituting for phi 2 and then getting it rho 1. So, phi 1 you will get as, I am sorry, let me explain this correctly. So, for phi 2 you have rho 1 phi 1 plus phi 2, and this you put it in I am sorry here rho 1 phi 2. So, phi 2 you will substitute as rho 2 minus rho 1 phi 1, and this you write it as equal to rho 1. So, by simplification you will get phi 1 is equal to rho 1 into 1 minus rho 2 by 1 minus rho 1 square. Rho 1 and rho 2 are known from the data. So, straight away you get phi 1. So, similarly you will get phi 2 as rho 2 minus rho 1 square by 1 minus rho 1 square. This is a simple algebraic simplification. I repeat again, when you solve the second order Joule-Walker equation, which we are doing now. So, you are solving the second order Joule-Walker equation to get phi 1 and phi 2. The phi 2 that you get is the partial autocorrelation of order 2. Remember that the phi 1 that you get here is not the partial autocorrelation of order 1. If you want the partial autocorrelation of order 1, you have to solve the Joule-Walker equation of order 1, which we did earlier, and then said that phi 1 is equal to simply rho 1. So, the phi 1 that you get from the Joule-Walker equation of order 2 will be different from the phi 1 that you get from the Joule-Walker equation of order 1. So, the phi 2 here is the PAC of order 2. So, in general phi p is the PAC of order p when you formulate and solve the Joule-Walker equations of order p. So, we now know how to determine the partial autocorrelations at different orders. So, p is equal to 1, p is equal to 2, etc. You know how to determine the partial autocorrelations of different orders from the data. From the data you will have all the autocorrelations rho 1, rho 2, etc., rho p, and look at the Joule-Walker equations. If you have rho 1, rho 2, etc., rho p, you will be able to form the autocorrelation function. You have the partial autocorrelation function here, and these are the autocorrelations up to lag p. So, all you need is the autocorrelations up to lag p to get the partial autocorrelations, and these we get from the data. You know how to get the correlograms. Let us see from the data. Let us say that you have the R 1, which is an estimate for the lag 1 correlation as 0.57, and R 2, which is a estimate for rho 2, which is the lag 2 autocorrelation as 0.07. Then phi 1, which is the PAC of order 1, partial autocorrelation of order 1, is simply equal to R 1. So, this is, you can put a cap here, this is phi 1 cap is equal to R 1, this is the estimate. Similarly, phi 2 cap I can write it as, these are estimates, sample estimates, because you are taking you are estimating rho 1 from the sample, and therefore, the sample estimates for the PAC are also denoted as phi 1 cap and phi 2 cap and so on. So, you get phi 2 cap is equal to rho 2 minus rho 1 square by 1 minus rho 1 square, and rho 2 is R 2 here 0.07 minus 0.57 square by 1 minus 0.57 square, which is minus 0.38. The partial autocorrelations, being correlations by themselves, will have a range of minus 1 to plus 1. They are also like correlations, they vary between minus 1 to plus 1 for all p. Now, we will see how we use the information on the partial autocorrelation. So, we have the information on the correlogram, we also have the information of the spectral density. Now, we have added one more information, which is that of that provided by the partial autocorrelation. So, just given the data, that means that you have observed data at a particular location. Let us say you are talking about observed stream flow at a particular location. First, we simply plotted the time series. We saw that there is a some kind of a indication of some regularity in the data. It may be just let us say the periodicity, or it may be an increasing trend, or it may be just a long term mean around which the values are fluctuating, and so on. So, you see, just by plotting the data as a time series plot, you get some indication of presence of some kind of a regularity. Now, this information we further smoothened, or we extracted much more information by plotting the correlogram. The correlogram may indicate presence of periodicities. That means, there is some periodicity that is indicated by the correlogram. It may be 12 month periodicity, 24 months periodicity, or long term decadal periodicities, and so on. So, the correlogram gives an indication that yes, there is a periodicity present in the data. We further fine tuned this information that is provided by the correlogram by plotting the spectral density. The spectral density brought to the fore the presence of periodicities much more strongly than did the correlogram. So, in the spectral density, we could identify that there is a periodicity corresponding to 12 months, there is a periodicity corresponding to 6 months, 4 months, and so on. In the example that we solved before coming to the ARIMA models. Then we also examined how to test these periodicities, and now we have introduced the partial autocorrelation. So, which means that we are going deeper and deeper into the information content in the observed time series. So, the basis for all of this is just the observed time series. You may have one time series, you may have several realizations of the time series, but we are simply going deeper and deeper into what information can we extract out of the observed values that we have. So, the partial autocorrelations are another source of information from the data, observed data. So, much the same way we plot the correlogram, we should be able to plot the partial autocorrelations also. Now, with all this information, we should be able to build models for the particular process. Let us say you are talking about stream flow, monthly stream flow at a particular location. So, we have extracted all the information that is contained in the data. We must use this data to build models for that particular process. The specific models that we will be now discussing, as I just mentioned, are called as the ARIMA models, auto regressive moving average models. Now, these are the specific type of models that I will be discussing are called as the Box-Jenkins type of time series models. They are written for stationary time series. So, the models that I will be discussing are all only for stationary time series. There are also non-stationary time series models. They are beyond the scope of this course, but keep at the back of your mind that much the same way we develop the stationary time series models, you can also develop non-stationary time series models adapting different other methods. If the time series that we are dealing with is non-stationary, first you must convert the time series into a stationary time series and only then develop or apply these models. How do we identify that the time series is non-stationary? First, you look at the correlogram. For a stationary time series, the correlogram dies down very rapidly. In fact, in most hydrologic applications, you may see that the stationary the correlogram dies down after 3 or 4 lakhs or 4 or 5 lakhs in most of the cases. By correlogram dying down, what I mean is that the correlations become insignificant as lag progresses with progress in lag. They become quickly insignificant, whereas if you have a non-stationary time series, the decay in the correlogram is not very fast. It may decay very slowly over a long period of time. You may see that the correlations become insignificant. So, this indicates, as you can see here, there is a significant periodicity that refuses to die down even with significant lags, and therefore, it indicates that the time series is in fact non-stationary. So, first you need to identify whether the series is stationary or not, and then only apply the time series procedure, the ARIMA models that we will be discussing henceforth. So, let us summarize now what we covered in this lecture. So, we started with the spectral density, the problem that I was discussing in the last lecture. We saw that in the monthly time series of stream flows that we considered for the example, there were significant periodicities which were shown primarily by the correlogram. The correlogram indicated a sinusoidal oscillation, and therefore, thereby indicating that there are periodicities present in the data. The spectral densities, the spectral analysis brought much more strongly the presence of periodicities, but also it also identified where exactly the periodicities are present. In the numerical example, it identified that there was a periodicity corresponding to 12 months, there is a periodicity corresponding to 6 months, 4 months and 3 months. Then we examined which of these periodicities are in fact statistically significant by doing the statistical test. We saw that all the periodicities were statistically significant in that particular example. Then we saw the effect of standardization. We standardized the series and saw that all the periodicities that we had identified as statistically significant were absent in the standardized series, indicating that standardization is one way of removing the periodicities. Then we went on to write the autoregressive moving average models, autoregressive integrated moving average models. So, the ARP model we wrote and then explained the auto regression process itself versus the regression model that we are used to. Then we introduced the concept of partial autocorrelations. The partial autocorrelations indicate the explanatory power of a particular variable x t minus k on x t when the dependence of x t on all other terms has been removed. And then we defined a general autoregressive integrated moving average model. So, we will continue with this discussion in the next lecture, where we will write a more general autoregressive integrated model, integrated moving average model, and then see the various steps involved in fitting a ARIMA model, general ARIMA model to a particular hydrologic process. So, we will continue the discussion in the next lecture. Thank you for your attention.